Okay, so that is a problem that we're going to be solving today, and here's the picture that goes along with the problem. And then up here I made a list of the different values that we're working with so that when we start to substitute, it's easier to just see them all up here and substitute quickly. So we know that theta is going to be 30 degrees because that is the angle of the roof. V0, which is our initial velocity of the ball, is going to be 9 meters per second. And remember that this velocity is in the direction of the travel of the ball. And finally, we were given our initial y value, or we were given the height of the roof, and we're going to call that our initial y, because if we call this y0 and this y final would be 0 meters because the ground is at 0 meters, and y0 would then be 8 meters above the ground, so we're going to call it 8 meters. So we'll put a box around here to keep it separate, and then we can start solving the first part of the problem. So first, we're just asked to break up the velocity, the initial velocity, into its components, and we're going to use those components, the x and the y, in our kinematics equations later on when we're solving for different values. So the way we're going to use this is with trigonometry. So you first want to draw what we were given, and then what we're solving for. So this is our 9 meters per second, which the ball is traveling at. We know that the angle here is 30 degrees because it's the same as the angle of the roof. We know that because this is on a standard coordinate axis, the x-axis, this is going to be our v0x, or the initial velocity in the x direction, and then this is going to be our v0y. Now it's important to remember that this velocity is negative, so we're going to want to put a negative sign here so that we can factor that into our solving and we don't forget about it. So now all we have to do is use trigonometry to find these. So to find v0x, we're going to use cosine of 30 degrees. So we'll say cosine of 30 degrees. Now cosine is adjacent over hypotenuse. So the adjacent value to this angle is v0x, and then the hypotenuse is 9 meters per second. So then all we have to do is solve for v0x. And then when we multiply, we find that v0x is equal to 7.794 meters per second. And then to find v0y, we're going to do the exact same thing. We're going to say, but instead with sine. So sine of 30 degrees is equal to, sine is opposite over hypotenuse. The opposite value to this angle is negative v0y. And our hypotenuse is 9 meters per second. Do the same thing as we did here, multiply to get v0y on its own. And then when we multiply that out and bring the negative sign over to the other side, we get that v0y is equal to negative 4.5 meters per second. Okay, so we've done the first part of the problem. I'm going to add these values to our list up here and then erase this part of the problem so we'll have space for the next parts of the problem. Okay, so the next part of the problem, they want us to find the time that it takes for the ball to reach the ground right after it passes this y0 point, which is the edge of the roof. So to do this, we're going to start with a basic kinematics equation. You should be familiar with it. And it's that y final equals y initial plus v0y times t, which is your time, minus 1/2 gt squared. And we're using this formula instead of the one on the x-axis because we have a y position, but we don't have any x positions. So that's why we chose this formula. So now we can start to plug in our values. So we said that y final is 0 meters because it's at the ground level. So we're going to say 0 meters equals 8 meters, which is our y initial, plus v0y we found is negative 4.5 meters per second. Negative 4.5 meters per second times t, which is the variable we're solving for, minus 1/2 g is 9.8 meters per second squared times t squared. And when we rewrite that, we'll see that 0 equals 8 meters plus, or minus, because we have that negative v0y, negative 4.5 meters per second times t minus 1/2 of g is 4.9 meters per second squared t squared. Now, this formula cannot actually be solved by factoring or anything like that. So unfortunately, we're going to have to use the quadratic formula. So I'm going to rewrite this up here so we'll have more space to do the quadratic formula. Okay, so I've copied the formula that we'll be using with the quadratic formula, and then I also wrote down our a, b, and c values that we'll be plugging into the quadratic formula just to make the substitution a little bit easier. So the variable that we're solving for is t. So t is equal to negative b, which would then be positive 4.5, plus or minus the square root of b squared, negative 4.5 squared, x equals negative b plus or minus the square root of b squared, minus 4 times a, which is negative 4.9, times c, which is 8, all over 2 times a. And when we solve this, we find that t equals either negative 1.81 or 0.8975. This actually continues out, so it's going to round. So we're going to call this 0.90. It's a little bit hard to round either way. So we have two values, but we can see here that one of them is negative, and time can never be negative. So we automatically know this answer is possible. So we can see that the only possible answer for time is 9 seconds. So finally in this problem, we're asked to solve for the horizontal distance that the ball will be from this wall when it hits the ground. So let's go ahead and do that. Now, this problem is maybe a lot easier than you may think it to be. We're going to use an equation that's just disguised as something that you've probably been using since middle school, and that is distance equals rate times time. The distance is the final distance, the horizontal distance that the ball will be from this point. The rate is just the initial velocity in the x direction, and the time is this time that we've already solved for. So to put it in the terms of the variables that we've been using, we're going to say x final, technically it's x final minus x initial, because it's the total elapsed distance, equals your rate, which is v0x, times the time. But since our x initial point is right here, and we're going to call this point 0, and then the ball is going to continue in the positive direction, this x0 point is really not, it's just a 0, so it won't be there. So we're going to say x final equals v0x times t. When we substitute, we get x final equals v0x 7.794 meters per second times our time, which is 0.9 seconds. And then when we solve that, up here we can see that x final is equal to 7.015 meters. So from this point, which we're calling 0 meters, it continues this way and will land at 7.015 meters from this point. And now we have solved the problem.